welcome to our final topic in Chapter 5, where we're talking about conditional probability and independent events. So let's jump on in. We're going to be doing some of our math in this topic as well as understanding what a tree diagram is. And you're going to hear me say that word and stumble through it a million times because I can't say it fast. Tree diagram. So anyway, what you're going to be able to do is calculate and interpret conditional probabilities using our multiplication rule. And of course, if you need to, you're going to use your tree diagram to model it. It can also show you where you're going to do your calculations as well. We're also going to understand what an independent event is, and we have another example right there. And of course, using the multiplication rule for independent events as well. So consider a playing card deck. And let's say I throw out a deck of cards and I ask, what's the probability of selecting each type of card? Well, in a deck of cards, it would be 1 out of, 52. Well, if I want to know the probability of selecting a specific number, if I want to know the probability of 8, then that would be, 4 out of 52, et cetera, et cetera. But what if I've already drawn an 8 and I want to now know the probability of either drawing another 8 at random or drawing a specific number, like let's say the ace. Okay, then this would be called conditional probability. Okay, and by the way, I want this deck of cards, so I'm going to buy it. Isn't that the cutest little dog you've ever seen? Okay, sorry, continuing on. The probability we assign to any event. So here's a formal definition of conditional probability, blah, blah, blah. But the reality of it is this is the information down here that's most important. How do we represent it and how do we talk about it? So if I have some condition A, I have drawn card number 8. Then this would be our event A. And if I want to know condition B, event B, I draw an ace next. So this would be our ace. This would be card number 8. Then this would be, how we denote it would be the probability, and in my subset, it would be B bar 8. And what that stands for is, what is the probability that event B happens, and here's our phrase, given that A has already occurred, or under the condition that A has already occurred. So this is what we call conditional probability. It's when an outcome can occur because of another, so it's sequential. Okay, so here's the math behind it. So to find the probability of A having occurred because B has already occurred, or A given that B has occurred, you take the probability of the intersection of A and B and divide by the probability of B. To find the other way around, if I want the probability of B given that A has already occurred, I take the probability of the intersection of B to A and divide by the probability of A. That seems kind of chaotic, but let's just dive on in and do a problem for ourselves. So, excuse me, we have this two-way table comes from page 321, and just a summary of this study. There were 10,000 students at some university who received course grades that semester. So that means they either got an A, a B, or below a B, but they didn't get no credit or dropped credit or withdrawal. So they got an actual course grade. So of these 10,000 students, some belong to the liberal arts college, the engineering and physical science that we're going to call EPS, and the human and health services college. And then they categorized them by, did you get an A in the class, a B in the class, or below a B? So we've got 3 questions here. They want us to find these 3 probabilities. But before we can talk about these probabilities, let's define our events. So event E is the grade comes from an EPS course. So it comes from this college, this school right here. Event L, the grade is lower than a B. And so this first question is easy enough. What is the probability that L occurs? What is the probability that of the 10,000 students, I have a grade lower than a B? That's easy. But what about these two? These are conditional probabilities. So this is saying P, the probability of E given that L has occurred. So what is the probability that my grade comes from an EPS course given that I'm already looking at the students whose grade is lower than a B? So this is no longer talking about the entire 10,000 subset of students. It is just talking about event L. That means I'm just looking at students with a grade lower than B. So this total value is actually what we are defining as our outcome set. So then here we have the probability that L has occurred given that E has already occurred. So what is the probability that I'll have a grade lower than a B if I'm already coming from an EPS course? So that would be this total right here that would help us out. So let's actually do that math. So to do that, I first need my totals. Then the first one's easy enough. 3,656 divided by 10,000 gives us a probability of 36.56%. That one seems reasonable. But what about conditional probability? All right, so let's look at this one more time. This is the probability of E given that L has already occurred. So here's our denominator. We could kind of see this as our fraction symbol. So here's our denominator. L would be that grade is lower than B. So this is my new denominator. And I want to know that the grade comes from an EPS course. So this is my new numerator. So it should look like 800 over 3,656. Ta-da, we have a percentage of 28.88%. My third option is to find the probability of L given that E has occurred. So what is the probability that I would get a grade lower than a B if I already am looking at the subset of students who have grades coming from an EPS course? So if I'm looking at the EPS course, then that means this is my new denominator. And again, I just want to know that grade is lower than a B. So this is still my numerator. And here we have 800 divided by 1600 gives us a probability of 50% or 0.5. So even though conditional probabilities can look scary, with a little bit of practice, it just becomes common nature. And you're like, okay, this is what I'm looking for. This is my denominator. This is my numerator. It's that simple. Moving on to our multiplication rule. So this is the formal definition, but if you want to know the layman terms right down here, this is a little bit easier to understand. For both of two events to occur, so our sequential events occurring, then you're going to multiply the first event by the conditional event of the second occurrence. So we actually have an example dealing with teenagers and their online activity, but before I can introduce that example, you have to know how to create a tree diagram. So this is kind of like that Venn diagram dealing with our Venn diagrams dealing with the events and complements and all of the disjointed and all that fun stuff that we did in chapter 5.2. And this one, instead of doing a Venn diagram, we're going to do a tree diagram because we have sequential outcomes. So that's the big difference. How do I know when to use a tree diagram? It's when I have sequential outcomes. What is the probability of getting this? Because that has already occurred. So our first example is consider flipping a coin. And if I toss a coin, what is the probability of getting heads twice in a row? And so the very first probability of tossing that coin is 50-50, half and half. And so then now that I'm at heads, what's again my probability of flipping heads? Again, it's half and half. But in order to get this tree right here, we're actually going to multiply the two probabilities. Again, this might feel like common knowledge, or it might recall from a probability you learned in a previous math class. And so we got our probability of HH was actually a fourth. But let's actually use this inside of a real world problem. So the Pew Internet and American Life Project found that 93% of teenagers, they polled students from 12 to 17, use the internet. Then they also found that 55% of those online teens have posted a profile on a social networking site. So this is a standard probability. And this would be our conditional probability, because how can you have an online profile if you're not on the internet? So my 55% is conditional to being a teenager who's online. So first and foremost, let us look at let's define our events, and then let's create a tree diagram. So I've got an event P of online, and I also have an event P of profile, but my profile event is not separate. It's conditional, so I'm going to do bar. The only way I can have a profile is if I am conditional to being online. So those are our two events. Now let's create our tree diagram. So I have a randomly selected teenager. I have a 93% chance that they are online and a 7% chance that they're not. Under the not category, I have a 0%, a zero probability of yes, because if I am not online, I cannot have a profile. Okay, and then I have a 1 perfect probability, 100% chance of not being online means I don't have a social networking profile. This side makes sense. Okay, let's go back to the positive side, the side we actually care about. So we're 93% chance of yes being online, and then if I'm online, I have a 55% chance of having a social network profile, which means it's opposite. I have a 45% chance of not. You can clearly see what your multiplication is going to be with this tree diagram, but let's go to our actual multiplication rule. Our multiplication rule says you're going to take the first event and multiply it by the conditional event. So we did that right here. We have online and have the profile, means I'm going to multiply my online by the conditional profile. Ta-da! We have a 51.15% chance that teens are online and have posted a profile according to the Pew Internet and American Life Project. And that's an actual study. You can Google that yourself and read up on it if you'd like to. Moving on to our last concept of independence. So when two events can happen interdependent. So like just because this has occurred doesn't mean that this has to happen. With the internet example, that couldn't be a truth, but we have an example regarding the Space Shuttle Challenger, and so we'll see that in just a second. In this instance, if our events are truly independent, then our multiplication just becomes multiply event A by event B. It's that simple. For example, the coin toss, okay? Just because I flipped this coin the first time around and I got heads, my second flip has nothing to do with my first flip. So that's why a half times a half, those were independent events, was our math behind it. So here we have our space shuttle. So the Space Shuttle Challenger disaster was determined to be a failure of the O-ring joints in the shuttle's booster rocket. Under cold conditions, it's estimated that the probability of each individual O-ring joint would function properly was a 97.7% probability. So what is assuming that the O-rings succeed and fail independently? So joint one can succeed and all the other ones can fail, or vice versa, or whatever. So what is the probability all 6 are going to function properly to prevent a Challenger disaster, right? Okay, so if the probability of joint 1 is okay, joint 2 is okay. So here are 6 events. This is a verbal statement. We didn't declare them as letters. I think that would be more time anyway. And so we're going to use our multiplication rule to do this. So this is not conditional, so you're just going to multiply each event by each other. And so that's what this represents. Well, what is the probability of each event? It was 0.977. We were given that information. Isn't that nice and easy? So it literally becomes 0.977 raised to the 6th power. And here you have it becomes 0.87 percent, or 0.87 or 87%. So there's an 87% chance that the shuttle would launch safely under similar conditions. So a 13% chance that it wouldn't. If this was the true math behind a NASA event today, I have a feeling that that would not be a high enough level of error for them to say, let's launch this shuttle. And so they might have to rethink what they're doing. And this is kind of where we understand from previous space disasters, we learn and we progress, and our math gets better each time. But anyway, wrapping up what you just learned about, you learned how to calculate and interpret probabilities. Specifically, you use tree diagrams, and you also understand the difference between an independent event and a non-independent or a conditional event. And so when you have the conditional event, you multiply the event by the conditional. When you have independent events, you just multiply the events. It's that simple. All right, I'll see y'all in class, and good luck with your Moodle work.